All right, good afternoon, everybody. Happy Tuesday. So hopefully the exam last week went well. I'll probably have them graded sometime towards the end of this week since I had a lot of overlap going on this past weekend. But I saw a few submissions as they were coming in when people were submitting, and it seemed like I didn't see anything too bad from those few submissions. So um, hopefully the exam didn't go too bad. I mean, it was relatively straightforward from the homework assignments. There was maybe one or two questions I would say that was a little bit of um, outside the box a little bit. The rest of it, though, I thought was relatively straightforward from the homework. So I hope the exam went well. So I'll have that graded hopefully by the end of this week. And I'll have a new homework assignment posted probably by our Thursday's class. It'll be just doing stuff with B trees and I guess search trees and in general, so AVL trees and red black trees as well. Um, so last week Thursday was our exam. Last week Tuesday I had a lecture on B trees, and of course that day I was in the faculty senate meeting, so I couldn't teach that day live. But I had a YouTube video posted in my 477 YouTube channel, so I know it's a little bit up and down because we have on our WebEx, we have our recordings on WebEx Cloud, then we have our YouTube videos, and WebEx kind of updated suddenly, so it's not allowing me to really save to my desktop. And also at the same time, it's better this way because I think the school does not like it if I save my live lecture classes and post it up onto YouTube. So this way it's kind of maybe safer for me, in fact, to do it like that. But anyway, last Tuesday's lecture on B trees, which was I covered I covered insertion of B trees in live, but last week Tuesday the deletion of nodes in B trees, that one was in my YouTube videos. So check that video out. It's about an hour-long video, so it covers deletion for a B tree. So that kind of content will be on our next homework involving and also AVL trees and red black trees as well. So that's sort of the updates for right now. So I'm going to now continue with new material for today. So let's go ahead and go back to the board. Screen one. Okay, so this is actually sort of from last time's last video's lecture. So I'm going to just sort of create a new board here. I'm going to call this one priority queues. Spell priority queues. So maybe I'll use the lines so it's easier to write stuff. Okay. So you might have learned about priority queues back in CS302. So I'm going to kind of recap that a bit just in case if maybe it's been a while or you forgot about it or whatnot. But then we'll go over a priority queue which is going to be different from CS302. So first we'll cover is going to be, sorry, this color pen. I'm going to go over, talk about, I guess, a binary min or max heap. I'm going to close Discord just because sort of just close Discord because I don't need any weird things popping up during class. So a bin, min, or max heap. So binary min or max heap, sorry. So it's going to be a binary tree. And we're going to implement this using an array. So same method like we did for CS302. So obviously, what we're going to do is we're going to have sort of index 1, is how I did it for CS302. Index 1 is a root node, a root element, I will say, root element of our tree. And we have a very simple method of being able to compute the parent and left and right children. So the parent will always be, it's always going to be at the index divided by 2. And since we're going to use integer types, then dividing it by 2, as always, we'll just do a integer division. So 5 divided by 2 will be 2, and 4 divided by 2 also be 2. Pretty simple. And the left child for any element is going to be always at index, multiply it by 2, and the right child will be at index, multiply it by 2 plus 1. So there's that. And of course, the way we actually maintain a priority queue is that the parent has the higher priority than its 2 children, or 1 child. If it has no children, also good enough. So the priority depends on if it's a min heap, then the parent will have a smaller kind of key value than both children. If it's a max heap, then the parent will have a larger key value than both children. So the priority depends on whether it's a min or max heap, whereas if for a min heap, the higher priority is a smaller. The smaller you are, the higher priority you have. And for a max heap, the larger element has a higher priority. So basically, in this case, the root element always contains the highest priority among all the elements in our structure. So for a min heap, the root contains the smallest element, and for a max heap, the root contains the biggest element. So in other words, the root contains the highest priority element among all the elements. So that's how we think about this. So priority queue, I guess some sort of examples of priority queue would be something like, I guess, like a line in hospital. So if there's a queue of people who are waiting to see a doctor in hospital, let's say somebody enters a line later, but their sort of situation is much more serious, they sort of move up in the line. So a regular first in, first out queue is good for a grocery store because, well, the last person that enters the line is the last person to be served. Whereas for a hospital, for a doctor appointment, or I guess hospital, often, it also depends on what condition you have. So you may have a higher priority, so you may move up in the line or in the queue. So that's kind of one example. But really, a priority queue is mostly used for various greedy algorithms. So the main use, at least for this, for our course, priority queue queues are used for sort of for several, maybe for all, I'm going to say several just to be safe, for several greedy algorithms. So the idea is that so a priority queue is like the enabler. It allows greedy algorithms to actually perform quickly because the priority queue always has the smallest or biggest element at the root. And for greedy algorithms, you always want to pick the next best move. So for Dijkstra's algorithm, Kruskal's algorithm, Huffman coding, all of those, we always pick the next best one. Although for Huffman coding, I don't think it uses a priority queue, but basically, all of those are greedy algorithms, which we pick the next best move every single time we iterate every step of the algorithm. We'll first start with binary heaps, just to kind of go into that. We'll go into binomial heaps and talk a little bit about Fibonacci heaps later on, but I'll start with this first, just to kind of be able to compare and contrast and sort of understand why do we prefer to use binomial heap over binary heap and so forth. So let's go ahead and we'll just go over binary heaps right now for today, at least for a part of today's lecture. So basically the way it's going to work is, so for a binary heap, whether it's a min or max, doesn't really matter. I guess we can use max heap. Yeah, we'll use max heap, sure, why not? So for a binary heap, we insert an element to the back of the structure or to the end of U, and we bubble up element as far as possible, far as possible until the heap order is achieved, I guess. Because you want to make sure if it's a max heap, you want to make sure that for every single node, the parent is bigger than both children. So inserting something to the back of the heap or back of the queue, it could violate this. You have to bubble elements up until you finally have our heap order once again. I'll sort of use an example just to recap this if in case it's been a while since you've done this. So basically for any type of a queue structure, it's always about inserting and removing is the two main sort of operations in any priority queue. So for a binary heap, for deletion, we essentially we're going to sort of we replace the root with the last element in the queue, and then bubble the element down until the order is achieved. Hopefully I wrote what was the correct grammar, but the idea is that after we sort of take the last element in our queue and put it to the root, there's no guarantee that's going to be a heap order. Very likely it will not be in a heap order. So you have to move that element down the structure, down this queue, until you finally have a min heap or max heap once again maintained. So that's sort of all there is to this. So let's go ahead, and I'm not going to do all the code, but I'll just go ahead and sort of give you an idea of how this actually works. So let's go ahead and just construct, or let's have an initial heap already given to us. So I'm going to create an array. Just like that would be good. Let's see how many should I have in this array. Let's create arbitrary amount of elements just because. Okay, now I guess these green numbers right there are going to be indices of this array. I don't want to put the brackets because that always takes so long to actually do that. So I'm going to use green numbers here as array indices. And make sure we have a mini heap. So we're going to have 8 elements. I'm going to just draw the tree version right below. I have maybe it'll be a max heap, I guess. Let's say 10. So I'll have 7, 5. I'll have maybe 6, 4, 3. So 1, 2, 3, 4, 6, 7. And I'll have maybe 1 over there. So this actual tree structure is how we can visualize it, but it's going to be stored in the array. So I'm going to go ahead and sort of I put that tree there first just to make sure I don't mess up this example. So at least the way I was sort of taught how to do min and max heaps is that the element index 0 is going to be just kind of nothing, index 1 and beyond, just so it's easier to, I don't know, at least easier to do all this, I guess. But either way, though, if you had that 0, it wouldn't be any harder. You have to sort of, the math would be a little bit different. So I'm going to scroll up for a second. Then this would be a little different. You have to sort of rework these two formulas, which wouldn't be a big issue, but for me, this is kind of simpler. Also this as well. So this and these to have to rework these, but these seem kind of to be very simple, at least to kind of work out. We want to trace these out, so I just will have always one VR root element. And notice that in the structure, the parent is always bigger than both children in terms of their values. So in this case, we use integers, but we could have any custom type, and just as long as we sort of have a way to assign priorities to each node, we'll have it. But we'll use integers now just to make it really easy. So when we actually have to work this out, we use the array version, but we actually visualize it, we use this tree to help us sort of see this. So if I want to go ahead and insert something into this structure, let's say I want to go ahead and insert, let's say, I'll insert 8 into this structure. So what we're going to do first is we're going to have to actually allocate one more spot to our array, which I'll do right now. Let's go ahead and just add this over here. This will be index 9. I'll put the value 8 over there, like that. So we insert the back of our structure. So in other words, the 8 would actually go right over there. So we have to maintain some index that always tells us where we are in the back of the structure, but I'll leave that detail out for right now. It's not too hard for us to visualize this. And bubbling up, we have to constantly compare to the parent. So for 8, its parent is going to be 6. And that's because we take index 9 divided by 2, it's going to give us 4, which will in fact be 6. Okay, I didn't make a mistake there. So 9 divided by 2 is 4.5, but we're going to have integer division, so 4. So parent of 8 will be 6. So we're going to have to bubble it up because we see here the parent is actually not going to be a larger, say the bubble is up basically. So 8 overwrites that, and the 6 will sort of move down. If you look at the array version, we're essentially comparing this element to its parent, and the parent is smaller, so we're going to swap these and put the 6 over there. And we have to keep on bubbling potentially. So we see here, we compare 8 to its parent, and the parent of 8 will be 7, because in this case we have 2 is the, index 2 is going to be the parent of 8 now. So to bubble this up once again, 8 goes there, 7 goes like that. Then we compare to its parent, and the parent of 8 is going to be actually 10. And we see here, there's no need to bubble up any further because now everything is okay. So the parent is now going to be larger than the child. So now we're good. Let's redraw this structure, and then I'll do one more insertion. I'm not going to do too much of it, just to kind of give us sort of a recap in case if you forgot how this works. So I don't want to spend too much time really on this. So I'm going to make sure I draw the right number of lines. So we're going to have, it's okay. Should be okay, I believe. Let's double check this though. I'll do one more insertion. That's it. We're going to have just 10, 8, 5, 7, 4, 3, 2, 1, and 4, 6. So we have this structure. If I redraw this in the tree form, we're going to have 10, 8, 5, 4, so let's 10, 8, 5, 7, 8, 7, 4, 3, 2, 6. So, of course, if I were to insert 11 into this structure, then what would happen is it would sort of go right over here. So I'm just going to put it here and I'm going to remove it. Just hypothetically speaking, if I put 11 right there, nothing would happen. We would insert to the back, and we would not have to, actually, no, sorry. If I were to insert 0, I made a mistake. So if I insert 0 into the structure, then what would happen is it would just go ahead and not bubble up at all, because the parent of 0 would be larger, so no work has to be done. So you have a case where insertion happens, and then you don't have to bubble up at all. But if I were to bubble up 11, however, or insert 11, sorry. If I were to insert 11 into this structure, and as always, we're going to have to insert 11 to the back of our structure. Go ahead and just call this go ahead and insert the shape. There we go. I'm going to insert 11 right here at the very end. So we're going to have index 10 would contain number 11. In other words, 11 is going to be left child of 4. We have to potentially bubble this element up. So again, same idea, we compare it to its parent. The parent of 11 will be index 5 because we divide index 10 by 2 right there. Bubble it up. So the 4 goes over there. 11 moves up. So actually, if we were to code this, use the array version, the tree is only there just to kind of help us out, help us visualize all this. Then I'll go ahead and keep bubbling up because the parent is still going to be not larger than 11. So you bubble this up. So we have to keep doing this work. So we're going to have 8 over here. 11 goes over there. I have to bubble up again because we can see here that the parent is going to be larger, or sorry, less than the child. And now we have our binary heap, max heap still preserved. So we have everything just in heap order. Let's go ahead and redraw this sort of tree, and then we can sort of do some analysis of this. Shouldn't be anything too bad, but let's go ahead and just first like this, set the shape, and just redraw this array afterwards, and then we can go ahead and do some analysis of insertion. See, we have 11 elements, so 10 lines are needed. There we are. Let's go ahead and just add indices over here. Try to not mess this up. So we're going to have 11, 10, 5, 7, 8, 3, 2, 1, 6, and 4. It's going to be our contents of our array. And of course, I'll draw the tree just so we can visualize this. That makes it better looking 7. We can visualize this. So we're going to have 11 and 5, 7, 8, 3, 2, 1, 6, and 4. So there we are. So we already have everything back in heap order. So we have to insert to the back and have to move the element up the tree because in this particular example, we're going to have it where the biggest element has a higher priority. So if you insert 11, that's going to move all the way up to the top of our tree. So let's go ahead and do some analysis of this, but this shouldn't be anything too bad. Let's go over the analysis of insertion. So basically, each bubble up step is actually pretty quick. We have to do many of them. So we insert an element to the back of the queue. Just like that. And then we have to bubble the element up the tree, I guess, or up the queue. Now for this, in the worst possible case, we have to bubble all the way up to the root. So in first case, we bubble the element to the root. Now, a binary min or max heap, so a binary min or max heap, doesn't matter which one we're talking about here, is always a balanced binary tree. So that basically means that at most we have to do the height number of bubble ups, and the height will always be log of n. So in the worst case, we have to do log n number of bubble ups. So that means the runtime is going to be O of log n for each insertion, because in the worst case, we have to bubble up all the way to the root. And we always go up one level every time we do a bubble up. So we're going to do exactly the height of the tree number of bubble ups. And since a binary min heap is always going to be balanced, then it's going to be O of log n for insertion. Let's go over a few examples with deletion, but hopefully there's no questions just yet. So nothing really too new, just mostly recapping from CS302. I'm going to copy this tree and use this for deletion. So I'm just going to go ahead and just do a simple copy here. Right. Benefits of using OneNote. So let's go ahead and scroll down here. And let's go over, is it really not going to work now? Okay, it's going to work. Okay, so let's go over examples of deletion. So I'm going to just put on a line here, separate all this. So for notes, I guess, will be better to have this. Going to use that there, so that does work out nicely. So it's a max heap, so I'm going to go ahead and do this delete max, which has that function built into any kind of heap structure. So for delete max, well, what's going to happen is we take that last element we have, which is going to be in this case index 10, or is 4, is going to overwrite the root element. So we're going to take this 4, and we're going to overwrite the root with it. I guess bubbling down, I'll try to put this in a nicer spot. Let's see if I can do like the 4 over here. Maybe it's a little bit easier to see that. Okay, anyway, we put the 4 right there. They bubble down this element. So we see here, we have 2 children for this node 4. So we always want to, for a max heap, you want to pick the bigger child, which is going to be 10 in this case, and bubble down with the bigger child. In this case, 10 is the bigger child, so we're going to bubble down with 10. 4 moves down, 10 moves up. So we're going to have to sort of move it like this. So 10 goes over there, and 4 goes right there. Got to keep on doing this, so we have to keep working here. So we have 2 children for 4 now, 7 and 8. The bigger child is going to be 8, so you have to bubble down the bigger child. So 4 goes over there, 8 moves up. So we have to go ahead and compare it to the bigger child. So for this index 2 element, it has 2 children, one at index 4 and one at index 5, because we do 2 times 2 or 2 times 2 plus 1 to get these 2 indices. Out of these 2 elements at index 4 and 5, 8 is the bigger element, so we swap with that. So 8 would go over here, and 4 goes over there. Now, for this element here, where 4 is, multiply it by 2 will give us 10. But now that since we removed the element from our structure, 10 is no longer part of our heap, because right there, this element 4, which is right here, is not part of our heap anymore. So we're done bubbling down, because we hit a leaf node. So right here, where 4 currently is right now, it's a leaf, because left child is not part of our heap, because we just removed that element from the heap, so it's no longer there. So this 4, which is right over here, this 4 right there, is a leaf node. So we're not going to have to bubble down any further. So our structure now looks like this. Go ahead and do a few examples of this just to kind of recap. Heap. Let's go ahead and just this right here. 7.5, let's say 9 elements, so 10. So lines are needed. Awesome. Let's do one more example of this, and then we can sort of do analysis. So it shouldn't be anything too bad. Hopefully we're all kind of keeping up with this. So we have 10. So I'll put 10 index 1 actually. So 10, 8, 5, 7, 4, 3, 2, 1, and 6. That's going to be our new array after we're done. So this tree is mostly there just to help us visualize it, but the actual algorithm code would actually go through this array. and we can very easily compute every element's parent position and left and right child position. So the array is more preferred to implement this, but the tree is there just to help us visualize. So now we'll have one more deletion. Then we can go ahead and do analysis. So now 8, 5, 7, 4, 2, 1, 6. So now I'm going to go ahead and do a delete max again. So once again, actually, before I even do that, if you want to get the max, it's very simple. It's always going to be element index 1. So getting the max is always a very simple process. Just return the element at index 1 in the array. Easy. So that's just a quick sort of shout out to that. Let's go ahead now and do a delete max one more time. Just to sort of, I guess, maybe do more than one example, I guess, is a not so bad idea. So then what's going to happen here is this element at index 9 is going to get erased, and we're going to overwrite the root with this element. So we erase this and write the root be 6. We have to bubble down this 6 element. So we have two children for 6, 8, and 5, which we can see here at these two positions, because we can simply use this formula to compute the left and right child positions in our tree. So we have these two children. The bigger child will be 8, so we're going to bubble down with the bigger child. 8 moves up. So if we look at this version over here, just sort of swap. So 6 sort of moves down a level. Then we're not done yet because there are still more children for 6. So we have two children, 7 and 4. And 7 is the bigger child, so we're going to bubble the 6 down with the 7. Just like that. So we're going to compare it with the left child. So 7 goes up, 6 goes down. And then at this point now, we have only one child, because if I take this index 4 multiplied by 2, it will give me 8. But then so 4 multiplied by 2 plus 1 gives me 9. But this element is no longer part of my structure. This element is no longer in the heap anymore. So this element is not there. So we have one child actually for this node that contains 6. And the child of 6 will be this value 1, because we'll apply this 4 by 2 to give us index 8. So we know the child is right there. And since this parent is actually larger, we don't have to bubble down any further. So we stop once we hit a leaf node, or if we have a case where one or both children are both less than the parent, then we don't have to bubble down any further. Go ahead and I'll redraw this, and then we'll be done with the example on deletion. 8 elements, okay. We're gonna have, let's see, we're gonna have 8, 7, 5, 6, 4, 3, 2, and 1. And I'll draw the tree as well, just so we can visualize it, but here's how our structure looks like now. We have 8, 7, 5, 6, 4, 3, 2, and 1. There we go. As we can see, everything is in heap order, just fine like that. So okay, so that's sort of the insertion deletion for a min or max heap. We're doing the max heap in this case. Let's go ahead and do some analysis of this. So analysis of deletion. So once again, very similar to insertion, is a little different, I guess. So we're going to basically take the last element. So last element okay, hold on, I can actually write this a little better. Sort of replace the root with last element, that. And let's see here. And then remove last element from the queue. So both these takes constant time to do these, so there's nothing wrong there. Then we have to bubble down the element that replaced the root. And then we have to, so we're gonna have to sort of bubble down all way to a leaf in the worst case. So once again, the worst case, we have to go all the way down the tree. So we have to do the height of the tree number of steps. So because of that, and of course, the binary tree, a binary min or max heap will always be a balanced binary tree. So the runtime is O of log n. So again, where n is the number of elements you have in your structure. So since the height of this tree will always be log of n, then the worst case scenario, we have to do log n number of steps to bubble down the element from the root down to a leaf. So that's kind of the preliminaries there. So next thing I'm going to do now is go over, well, how do we actually construct a min or max heap? So we'll focus on max heaps, I guess, for right now. So if we're given a set of elements, let's say, so let's go ahead and just make another note here. So construct a min or max heap given a set, given an array. So this array is not for sure going to be in heap order, but we're just simply given an array, just like that. We're given an array, and you want to construct a min or max heap out of it. So one option we could do is we could allocate another array, which is going to be the heap array, and insert an element one at a time from the given array into the heap array. And every time we insert into our heap array, we're going to have to bubble the elements up every single time we insert. So each insertion will take log of n time. So this is going to take, so this approach takes O of n log n time. And we can be very specific about how we do this, but really it's going to take log of 1 plus log 2 plus log 3 plus log 4 as we insert. And if we go ahead and sort of do a summation on that, it's going to be n log n. So that's going to be sort of the runtime to do this. So because we're going to have to insert every time we're going to have to bubble elements up, which takes a log of n time. So we can sort of see it's n log n, which it does work. But there's actually a better way we can do this. So I guess maybe for today, maybe if I cover binomial heaps later, the idea is that sometimes being lazy is actually not a bad idea in computer science theory, which is actually very bizarre. But here's a case where instead of actually every time we insert, what if we can sort of, do fewer bubble ups? And because certain nodes will do not so much work and certain nodes do a lot of work, but if we sort of combine average all that time together, it's going to actually give us sort of a very nice runtime. So what we could actually do, a different approach could be, is we could say, well, we could, so we can use the given array and bubble down from starting from the leaves, starting from all way to the root. So we could do that actually. Let's go ahead and do an example of this, see how this actually would work. So I'm going to just create some arbitrary array, which will not be in heap order, but just some arbitrary array I'm going to create. We'll first do an example to see if that actually does work, and then we'll go ahead and analyze its runtime. So I'm going to just pick some arbitrary size array, like that. And we'll assume that the user will give us the array where index 1 will be our first element. But of course, we always can shift the elements over by 1, no problem. So we'll have index 1 will be our first element just because. I'm going to have maybe 5, 3, 6, 5, not 5, I'll use maybe 10, 2, 7, 8, 1. So you can see here, this is not going to be in heap order. If I were to draw this in the tree version, so you can visualize this array, you would have, let's say, 5, 3, 6, 10, 2, 7, 8, and then 1. Like that. You can see here it's not in any kind of heap order. So we'll assume max heap just to be consistent. It's definitely not in max heap order. So of course, I could take each element, 5, insert it to a heap, then take 3, insert it into a heap, and so forth, which I did in the first step, which will definitely work. But how about we actually bubble down from the leaves, actually? Let's go ahead and see how that actually would work. So right now, looking at 1, well, 1 has no children, so we're good. No work has to be done there. Let's look at 8 next. So we first look at 1. I look at 8 next. Kind of iterate from the right to the left in our array. We check 8. There's no children for 8, so nothing to be done here. Then we'll check 7. Nothing to be done here because no children. So far, so good. Let's look at 2. Nowhere to bubble down because there's no children for 2. Same thing for 10. Well, we have 1 child, but it's less than 10, so we're good. So right now, this part of our tree, this portion is in heap order so far. Everything above might not be in heap order, but this is in heap order so far. So now that we have a heap order, we're kind of level by level going to construct our heap. So now next element after 10 will be 6. And we see here, well, we don't have a heap order. So we have 2 children, 7 and 8. I'm going to bubble down with the bigger child. And now this subtree right there is going to be in heap order. And now what's going to happen is we're going to have, okay, so we have 3, so we have this next element right there, 3. It's not in heap order, so we have to compare it to its 2 children. 10's the bigger child, so we're going to have to bubble the 3 down like this, and then 10 moves up. So now everything up to this point is all going to be in heap order. So you can kind of see almost inductively how this is actually kind of step by step going to work. So you're assuming that the elements below are in heap order. If you bubble down for the level above, the level above is going to be also in heap order if you think about this inductively. So now, okay, everything at that point is all in good heap order. Now we have to bubble down from the final elements. I'm going to use a red pen to sort of not confuse these. So now to bubble down from the roots, we have two children of 5, 10, and 8. We're going to bubble down with the bigger child. So 5 goes over there and moves up. We have two children of 5, 3 and 2, and they're both actually less than 5, so nothing to be done there. So there we go. Now we have our curve. Now we have our new updated, very messy looking binary max heap. Let's go ahead and sort of redraw this array. Copy this instead of copy this right there. That's all about. What's that here? Of course, I have to go somewhere. Picture, that's fine. Okay, so our heap now will look like this, or our array looks like this now. We're gonna have 10, 5, 8, 3, 2, 7, 6, and 1. And the tree version, I'll draw the tree right below, so a more cleaner looking tree. We right here, so you have 10, 5, 8, 2, 7, 6, and 1. And we have this. Looking at how the tree looks like, and we can see here, definitely max heap order. So this method does work. You actually can prove inductively that it will work because every level below, we can assume it's going to be always in heap order. And if you bubble up to the level above, then everything up to that level will now be in heap order. So you can inductively show that this is going to actually work. So this does in fact work, because assuming that we bubble down, we always have a heap order up to that level we bubble down from. So now, okay, so now we know it works. Let's go ahead and look at the runtime of this approach. So I'm going to draw a hypothetical sort of tree right here, just so we can see how the runtime analysis would go for this. Let's go over the runtime analysis. This is actually known, I think, of as build heap, of build heap, or heapify sometimes. I think build heap is the actual term for this operation we're doing right there, which is going to bubble down from the leaves up to the root. So let's go over and draw like an example tree over here, just so we can sort of, get an idea. We visualize, the actual amount of work. So see if I can draw all these. Hopefully it does look somewhat okay. Well, not perfect, but good enough. So we have this sort of array, and we're going to visualize the array in this sort of binary tree representation. We're going to visualize it like this. So basically, we want to count how much work is being done here. So at this level, right here, so this is going to be height of h tree. So right now, at the very bottommost level, at 2 to the power h, we're going to do 0 amount of work. I'll write this in blue over here. We do 0 work. Because basically, at the leaves, there is nothing to bubble down with. So we're kind of okay there. The level above, 2 to the power h minus 1, we're going to do each of these nodes. Every node in this level will do at most 1 bubble down. It has only one child to bubble down with, so it won't do any more work. So each node at this level, at 2 to the h minus 1, is going to do at most 1 bubble down. And then the next level above, 2 to the power h minus 2, will do at most 2 bubble downs. And at the root level, we're going to have essentially 2 to the power, 0. I'm just going to sort of just put that there, 2 to the power 0. We're going to do exactly, in this case, we're going to do h amount of work, or height of the tree amount of work. So we can see here, this is actually going to be somewhat of an amortized analysis over here. Let me go ahead and put that here. This is actually a form of amortized analysis, which we'll refer to this a little bit in the next couple of lectures. Amortized analysis, or amortization. So I'll first sort of show this example proof, and then I'll explain what does amortized analysis actually really mean. Let's go ahead and this is actually an example of amortized analysis, but I'll describe it in a second. So we want to count the amount of work to be done. So what happens is, every time you go up one level, we do one more amount of work. So every node above does one more amount of work than a node in the previous level did. But we only have half of the nodes every time you go up one level. And that's really the whole key to this runtime. So actually, the summation we're going to have is going to be the following. So we have, let's say, I equals 0 up to h. We have 2 up to the power h divided by 2 to the power I, multiply this amount by I. This all be in one summation. So all of this will be in the summation. And this kind of models that behavior above perfectly, the summation, because every time we increment I by 1, we divide that from our total. And so basically taking 2 to the h divided by 2 to the power I is the same thing as just saying 2 to the h minus I. It's the same sort of principle. So we can go ahead and sort of, remove some terms out of the summation. So I could do the following. I equals 0 up to h. I can remove 2h out of this and have I over 2 to the power I within our summation. So using different sort of known formulas, and also Wolfram Alpha can solve this as well, but there are formulas, in the Steve Siden's cheat sheet that will work this out. So this summation, so if I have, let's say, I equals 0 to infinity, I over 2 to the power I, this will actually equal 2. The summation solves to 2. So we're going to have essentially 2 up to the h plus 1 will be this entire amount, because this is basically going to be 2 times 2 to the power h will give us this amount, and this amount is relatively equal to n. This is going to be relatively equal to, I guess it'll be equal to O of n, because if you have a height of h for a balanced binary tree, number of nodes will be just 2 to the h plus 1 minus 1. So we're missing that minus 1 portion, but it's okay, it's close enough. So the amount of steps this approach will do is going to be n. So this build tree, so this is going to be the runtime for build tree, or build heap, sorry. So build heap has the following runtime. O of n. So if you bubble down from the leaves up to the root, it's O of n time to construct your heap. So it's definitely better than O of n log n. And it's amortized because, well, some of the, maybe I'll zoom out so you can see all this, but still clear on WebEx, hopefully. So basically here, the idea is the leaves, there are many leaves, but they all do very little work. And as we go up the tree, we do a little bit more work each time, but we have half the number of nodes every single time. So the root does the most work, but it's only one node over there. So the idea is that if we average out all the work that's being done, overall it's going to be O of n time. Because we have a lot of nodes, it does not much work. We have few nodes, we do a lot of work, but those few nodes doing a lot of work is not gonna really sort of overshadow the little work done by a lot of nodes. So it's kind of the whole idea. And it's actually an example of amortized analysis. So we'll do other sorts of priority queues that involve amortized analysis. Let's first sort of go over what is amortized analysis. So I'm not going to really go sort of that in depth with this with our analysis of different priority queues, but I want to first just discuss this. So think of, let's say you have a car and you have to go to school or work in one day. So of course what you could do is every day go to the pump and put in, let's say, $3 into the gas. So it's going to be about 1 gallon. Let's say you have to go, you live far away, so you have to go to school and to work. So let's say you do end up driving 30, okay, how about this? Okay, how about $2 per day? you drive around 20 miles in one day. Let's just say that for right now. I can't think of an example, but you drive 20 miles in one day, let's say. So $2 of gas per day is going to be enough to go 20 miles. So you could, of course, next day, again, go to the pump, put in $2 and drive every single day. And you're averaging $2 per day for gas. I don't think it's really accurate, but we'll just go ahead and go with that for right now. Because nobody actually does this. That's why it's kind of hard to visualize it. But let's say you're like a normal person, you don't do this because you don't have time to go to the pump every single day. And of course, if you go to a pump, then try and get out of, let's say if you go to a natural gas station, and you want to get out of the gas station, it's always such a pain because always people are driving around. So going to the gas station often is really going to really waste a lot of time doing it every single time. So one way you can do this actually, go to the pump. If you have the luxury, you can of course fill your whole entire gas tank up in one at once, which I didn't have luxury of that when I was a student ever. I guess I kind of have the luxury now. When I was a student, though, I had to put 10 bucks in per time every time and hope that I had enough gas to get around everywhere. But let's say you have the luxury of being able to fill up your entire tank at one time. So you put like 40 bucks into your tank. Let's say it's a good round number to use. So if you do that, then you have to go and put gas in every single day. So you have to put 40 bucks in at one time, but over time, next day and day after and day after, you're not going to be pumping gas in your car every single day. So those days, you don't put any kind of money into your car. So once the gas tank becomes empty, you got to put 40 bucks back in. So let's say after, let's say after 20 days, your gas tank is empty. Then what happened was you paid 40 bucks. After 20 days, it was empty. So you averaged $2 per day. You just didn't pay it all at one time. You didn't pay it per day. You actually paid it all at once, but you averaged $2 per day, sort of, gas usage. So amortized analysis is basically like that. So you pay up a lot up at certain moments, but then over time you do less work. So for this case, the root does a lot of work, but then the other nodes don't do so much work, and it kind of averages out to be a certain runtime. So that's kind of definitely a very complicated, concept in computer science, but I think it's kind of based off of like economics and so forth. But we'll do a little bit of just talking about this for different structures as we move forward. But this structure, this topic is kind of why we're going to go over other types of priority queues. So I'm not going to really go into heap sorts. I know on my syllabus it has heap sort on there, but I don't really want to go into that. So I guess for now, for heaps, just sort of know how to insert and delete and their runtimes, and know how build heap works and its runtime. That's all you have to really know for binary min or max heaps. We're not going to go over heap sort because that's from 302. I don't want to really get too much. I already spent like an hour going over mini heaps already as it is, so let's not go too further in this. So that was basically our binary mini heap sort of lectures. Any questions on any of that? So I'm going to go over binomial trees right now. So we'll go over binomial heaps in a second, but I have to first go over binomial trees before we can really do that. I don't think it's really covered in CS302. So a binomial tree. Let's do some notes on this. Make sure I have my notes right here. So it's going to be, I guess, a recursive structure, I suppose. It's a tree structure, of course. That's sort of the idea. Putting this together over here. So the idea is you have to sort of use smaller binomial trees to construct larger binomial trees. So it makes it kind of recursive in a sense. So the idea is we have different types of tree shapes. So let me go ahead and just try to sort of show this right here. So we have a tree, we have a BK tree, so binomial tree of size K. What we have to do is, well, essentially, I'll start from the beginning. So I'll just start here. So B0 tree is going to be just a single node by itself. And the B1 tree, we take two B0 trees and we combine them together. B0, B0, combine them. Then for a B2 tree, we take two B1 trees and we combine them together to make it into a B2 tree. A B3 tree, we take two B2 trees, this, and we combine them together, make a B3 tree. That's sort of the idea for how B trees really work. We just take any kind of BK tree, go ahead and write this down over here. So ideally, so here's a more theoretical explanation. So to construct a BK tree, we combine, I should say the right will be merge two BK minus 1 trees, making this process recursive because we take older ones to create newer ones. So it's for smaller trees to make bigger trees. So in general, we just have essentially our first, we have our BK minus 1 tree. We have another BK minus 1. And we're going to combine them together. This is going to be a BK tree. We combine the roots together, we link them together. That's going to be a BK binomial tree. So a few other notes I'm going to add here on binomial trees is that so the root, so I guess so for a binomial tree BK, the root node has degree K. So let's look at the examples above. B0 has a degree of 0. So a degree means how many sort of edges it has. So for B1, the root has only one pointer. For B2, this will be the root, will be right here, I'll draw. This will be our root node. We have degree 2. And for B3, that'll be our root, 1, 2, 3. So you have that pattern always for every binomial tree. Let's see what other notes we have here. So there are 2 to the K elements. And you can actually sort of show this also inductively because you multiply. So let's go ahead and sort of show why this is always going to be the case. So a B3 has 8 nodes. We have 4 nodes, we have 2, we have 0. So basically, the simple proof is that we take sort of, let's say for a B1 tree, we have 2 B0 trees. So we double B0, so it has 1 multiplied by 2 will give us 2. Then for a B2 tree, we have 2 B1 trees. So it's going to be B1 size multiplied by 2. So we double B1 to make this into 4. So B2 has a size of 4. We take 2 B trees. So two B2 trees, sorry. So 2 times B2 will become a B3. So we always double the previous tree. So we have 2 B2 trees make a B3. So That's why it's always 2 to the power k number of nodes. So for a B4 tree, we take two B3 trees. So we have to double the size of B3, so that's going to be a B4 tree. So we always double the previous ones. That's why there's 2 to the k elements. A very simple sort of explanation or proof on that. And then the height is k. So then we see right there that the number of nodes and the height is once again going to be logarithmic with respect to each other. So the height of a BK tree is going to be a logarithmic property. So if 2 to the k elements, if k height, that's definitely going to be log 2. So if you take log 2 of the elements, log 2 of 2 to the power k is going to be k. So we kind of have that. And then another interesting property we have. So yes, basically we can think of it as the root of a BK tree has children that are B0, 1, 2, BK trees. So if the root was eliminated, if you took the root and ripped it out of the tree, then all of those remaining trees are going to be B0, B1, B2, up to BK minus 1. It's a few very interesting properties, actually. I'm actually kind of looking at these notes right here, and it's actually kind of really a fascinating structure, actually, binomial trees. But anyway, that's sort of the properties of a binomial tree. So not really too hard to really construct these. So we're going to use this property to actually work with binomial heaps. So I'll use a binomial min heap for our examples just because it could have been min or max, but I'll use min just because my notes, I use min heaps just like that. So the whole idea is we're going to use this binomial tree structure to create our priority queue. And then the question is, well, first of all, why? It seems like a binary heap was actually good enough. I mean, there's no point really doing all of this. But the whole idea is that to merge two trees together is actually faster than merging two binary trees or binary heaps. Okay, fine. Here's another question. Why do we want to merge? I mean, who cares about that? Well, merging is nice because with merging, you can actually amortize the runtime of insert. Because if you amortize the runtime for a binary heap, it's going to amortize to log of n. Because let's say if I want to insert n elements into a binary heap. So let's say we're not able to actually just take our heap and just do a build heap. Let's say we're doing Dijkstra's algorithm. We have to insert one at a time into our structure, right? So if we insert n elements, it'll take n log n over all the time. If we amortize that, then average will be log n per insertion. We have n log n total time divided by n insertions divided by n, then our average amortized cost will be log of n per insertion. So doing this sort of merging of binomial heaps, and also, which I won't really go over this in that much detail, but having a lazy binomial heap will allow you to actually amortize the cost of each insertion to be relatively constant, which is much better than log of n. Now, in some cases, if you insert, it will take a lot of steps, but many insertions or many merges, if you will, is going to actually take not much time, and some will take more time, but if you average it all out, it's going to be overall a very beneficial runtime. So, in fact, for Dijkstra's algorithm and Kruskal's and whatnot, maybe not Kruskal's, but for Dijkstra's, they actually use a Fibonacci heap to implement this to get a better runtime than using a regular binary sort of heap. So I won't go too much into Fibonacci heaps, but I'll just sort of, give a little bit of a mention to that after we cover binomial heaps, sorry. And the next topic we'll cover is going to, in fact, be a binomial heap. I only have 5 minutes left over here, so I guess I can't really talk too much right now. So next time's class, we'll go over binomial heaps. So I guess for today, that'll be it. So I guess take care, you guys. Stay safe. Thanks for watching, and I'll see you guys next time.